Guys, safety's not a joke. Not really.
Hey guys, this is Alan, Cody, and David from Lamar University's Fluid Mechanics class, and we're making a laminar flow nozzle for you today in our video. Our build came from the King of Randoms video on YouTube titled Making a Laminar Flow Nozzle, and we have it posted in the description below. It's a pretty cool channel, go ahead and check it out. This was a fun project, and it only took us about 30 minutes to actually put together. As you can see, we do have our build process playing in the background sped up for your enjoyment. As far as the materials go, it only cost us around 25 bucks to put together. Now that said, I did have the power tools and some of the materials already, but you can still put one of these nozzles together for pretty cheap. For our materials list, check out the description below. We didn't deviate too much from the original build. Now that said, we did decide to go with a 3-inch pipe to save money. If you're going to deviate from the dimensions, just be careful because it will affect your Reynolds number. We kept the 5/8 outlet, but did use a 3-inch pipe, so that was just enough to get a laminar flow, as we'll show towards the end of our video. Laminar flow, as we will see, is when all the fluid molecules are moving in the same direction. This will produce a beautiful, silky, glass-like fluid surface. Conversely, turbulent flow is when the fluid molecules are not all moving in the same direction and will look rough and violent, similar to when you turn your sink faucet on full blast. You can quantify laminar flow by looking at the Reynolds number of the fluid flow in question. The Reynolds number is a convenient parameter for predicting flow condition and is simply the ratio between the inertial and viscous forces of the fluid. When the Reynolds number is less than 2100, you can expect a laminar flow. When the Reynolds number is between 2100 and 4000, the flow is in transition between laminar and turbulent flow. A Reynolds number above 4000 is turbulent. Our nozzle, specifically, has a Reynolds number of 1987 and is thus considered laminar. We'll be looking at the calculations after the build is complete. Until that time, go ahead and enjoy the video.
I've got wings now.
The old song, Sam.
Yes, ma'am.
It's been a long time.
In order to calculate the Reynolds number for our laminar flow device, we first need to calculate some numbers using our experimental data. First, we need the diameter of the laminar flow nozzle. It was measured to be 5/8 of an inch, but we converted it to metric units for further calculations. Using this diameter, we were able to find the area of the nozzle by using the formula pi over 4 dn squared. This process was repeated to find the diameter of the hose as well as the area of the hose. After that, we used a 5-gallon bucket to filling it with a water hose to find the volume flow rate Q. The time was 32.08 seconds. Using a 5-gallon bucket and the water hose, we were able to calculate the volume flow rate Q. After that, we used Q to find VH, which was equal to Q over AH. Once the inlet velocity was found, we then used the continuity equation AL/VL equals AH/VH to find the velocity at the exit of the laminar flow device, VL. We are now almost ready to calculate the Reynolds number. Using the temperature of the water, which was found to be 65 degrees Fahrenheit or 18.6 degrees Celsius, we are able to use our textbook to find the density and viscosity. The only thing left to do now is plug the numbers found into the equation for Reynolds number, which is RE equals rho VL dN over mu. Doing this, we found our Reynolds number to be 1987, proving our device is truly laminar.
Thanks for watching. Have a great day.